All right, here we are with the part 4 of the jeweler problem, the final part where we put it all together and finally answer this problem. We remember we have a jeweler that makes necklaces and rings using gold and diamonds, 5 gold and 5 diamonds in every ring, 15 gold and 3 diamonds in every necklace. There are only 1,200 units of gold and 720 diamonds available. The rings sell for $20,000, the necklaces for $40,000. How many of each should she make to earn as much money as possible? First thing we did back in part 1 is we set some variables. We used X for the number of rings and Y for the necklaces because those were the only things that were not determined by the problem. We wrote 2 equations, one for the gold, one for the diamonds. We took those equations, we graphed them. This is the gold equation that we graphed, and what I've done here is I have shaded everything above the line because as we move to the right, that's making more rings, and as we move up, we're making more necklaces, and eventually we're going to run into that line where we've run out of gold by making either too many rings or too many necklaces. So everything in that orange area, we don't have enough gold to get there. Here's the line for the diamonds. And again, we've shaded that, everything above that line, saying, well, we don't have enough diamonds to make this many rings or this many necklaces. We put them together, and we've got this. This is kind of where we ended up last time, but now we shade a little bit to see that those are the regions that we actually cannot reach. In this orange region on the left, we have plenty of diamonds to get there. That's below the blue line. That's okay. We just don't have enough gold because it's above the orange line. Down at the bottom, we've got this blue region where we have plenty of gold, but we've run out of diamonds. The whole upper right is where we don't have enough gold or diamonds. And then we've got this white part down in the lower left corner where we do have enough gold and diamonds, and that's where we're going to be looking for our answer. By the way, we can't make negative rings or negative necklaces, so we're going to go ahead and shade all the negative areas under the x-axis to the left of the y-axis because we can't find an answer there. You just can't make negative something. So we zoom in on this white region. The answer to this problem has to live somewhere here. Every possible number of rings and necklaces that we can make with the supplies we have is somewhere in this white area. We call this the feasible region. For example, say the jeweler wants to make 70 rings and 50 necklaces. Is that possible? Well, yeah, we go over to 70 on the x-axis, up to 50 on the y-axis. That's in the white area. That's possible. We do have enough gold and diamonds to reach that solution. What about 100 rings and 50 necklaces? Well, if we go over to 100 and up to 50, we see that that is above that gold line. We are in that orange area where we don't have enough gold to make that many rings and that many necklaces. What about 30 rings and 70 necklaces? Yes, just barely. That's on the line, which means that just as we make the very last ring or necklace to make 30 or 70, we're running out of gold. So that is a solution, and it's a good solution because we've used as much gold as possible, but we couldn't make one more of anything because we'd go over that line. So it turns out that the best outcome is always located at one of the corners of the feasible region. Proving that requires some math beyond this class, but you can trust me on this. So all we need to do is find out what are the coordinates of those 4 points, and then we check them to see which one is going to make the jeweler the most money. So we've got this lower left corner, which is 0, 0. That's probably not going to be the best one. We had our all rings strategy that we looked at the very first part, where we could make 144 rings if we didn't make any necklaces. We had the all necklace strategy, where if we made 0 rings, we could make 80 necklaces. And then we found out in part 2 and 3 that we had this mixed strategy, where we could make 120 rings and 40 necklaces, and that used up all of our gold and diamonds at the same time. So, remembering that rings sell for $20,000, necklaces for $40,000, we can plug those numbers in and figure out which one is going to make us the most money. So the 0, 0 obviously is $0. The all ring strategy, we do 144 times $20,000, and that gives us $2,880,000. Our all necklace strategy, 80 times 40,000 gives us $3,200,000, which is better. And then we've got this mixed strategy, 120 times 20,000 per ring times 40 plus 40 times 40,000 for necklace gives us exactly $4 million. Putting it all together in a table, we can see that the best strategy for the jeweler is to make 120 rings and 40 necklaces, coming up with a revenue of $4 million. And it's not a coincidence that that is the solution that lets the jeweler use up all the gold and all the diamonds at the same time and not have any supplies left over. If you think about it, it does make sense that that would be the best solution. Now, what if we add an additional constraint to this problem? What if the jeweler realizes, okay, I've got gold, I've got diamonds, but I also have time. It takes me 2 days to make a ring. It takes me 4 days to make a necklace. So there's this 2x plus 4y equals, well, 365 days in a year. There's this green line that I can't cross because I just don't have enough time to make that many rings and necklaces. And we shade above that green line green, say that's all the possible answers that the jeweler just doesn't have enough time to make. That changes the shape of our feasible region. We've added some extra corners here. Let's take a look at these. We've still got our all necklace strategy where we run out of gold. We know we run out of gold because it's on the gold line. We have our all ring strategy where we run out of diamonds. It's on the blue line, which is our diamond graph. And so that's how we know we're running out of diamonds. But right here, this is on the equation of the gold line and the timeline. This is where the jeweler runs out of gold and time at the same time. Still have plenty of diamonds left over. Over here, we've got a solution where, because it's on the blue and green, we're running out of diamonds and time at the same time, and we still have some gold left over. But what about this one? This was the best answer before. 120 rings, 40 necklaces, but this is beyond the green line now. We run out of gold and we run out of diamonds, but we don't have enough time. We can't actually use that answer anymore. We don't need to check that point because that's not one of the corners of the feasible region. It's not on the white region, which is where all the solutions live. So the 120 rings, 40 necklace solution we found before would not work now. We would have to go back and check those two new corners to see which of those is going to make us enough money. And the reason, or the way we would find the intersections between those lines, we would take those two lines, we take the equations, and using like the substitution or elimination method, we would have to use algebra to find the exact coordinates of those points. The graph's going to get us close and let us estimate. The algebra is going to get us the exact answer. Now, just one word. The way I've been graphing things where we shade the areas we can't get to is more of an Asian style of graphing. In America, they tend to say, you know what, we're going to shade everything in the area that is possible. So all the things we have enough gold for, we're going to shade the orange. And the blue is all the areas where we do have enough diamonds, and green is where we do have enough time. And you end up with this, and you find, well, let's find the place where it's shaded every possible color at once. This doesn't work for me very well. This one works a lot better for me. So maybe you could use that too, but just be aware that on certain tests, you might be expected to find where the shaded areas overlap instead of finding where there are no shaded areas. So to sum up, linear programming. We take our word problem, we come up with some variables, and we write some equations. We take those equations and we create a graph. We can shade that graph to find the feasible region, where all the possible solutions live. And then to find where the lines intersect, because those are the corners of the feasible region, we have to use algebra. We have to solve some systems of equations. Finally, we take each one of those corners, we take the x and y values, we plug that back into the original problem to figure out which one of those is the best solution. So that's the summary to linear programming. Hopefully that will get you through the rest of the problems, the baker problem, the toy maker problem, and the farmer problem. Good luck with that.